All right, so we're in our last flipped lesson for this unit, and we're going to be talking about what happens when waves interfere with each other. So before you watch this video, you should have completed Lab 4, which will give you a little bit of introduction into standing waves, constructive and destructive interference. So to start simply, let's talk about what is happening. So on this first picture on the right over here, I have a pitching machine, and these two pitching machines are pitching balls. B is going towards Alan, A is going towards Bill. And what happens is if these balls are in the same point in space at the same time, they collide and they ricochet off. So those waves, or those balls rather, they interfere with each other. But that's not what we get with sound. If I have two loudspeakers, sound waves can travel through the air, they can interfere with each other, but then they pass through each other as nothing ever happened. So both observers in this case would hear undistorted sounds despite the sound waves crossing. And that is the concept of what happens when waves interfere, and we'll get into superposition. So a really easy way to look at this is by looking at waves on a string. And now if I send, here's wave 2 and wave 1 and wave 2, you can't really see that, wave 1 and wave 2. Now these two waves are traveling at one another. When they're at the same place at the same time, they overlap, and this little wave 1 and this little wave 2 combine together to make this bigger wave. And then after that, wave 1 and wave 2 keep going as if nothing ever happens. So superposition is what happens when waves interfere. When two or more waves are simultaneously at the same point in space, the displacement, their amplitude, how big they are, at that point is the sum of each individual wave. And we can break this down into two main categories. So when we're looking at superposition, we know that the displacement is different than each of the individual waves. Now, we call this process interference. These are when the waves interfere with each other. So we have to look at the medium and we have to say what's happening when these waves interfere. Now, there's two types of interference. There's constructive interference. So constructive interference occurs when both waves have positive amplitude, so the total displacement is larger. Destructive interference is when the displacement of the medium where the waves overlap is less. So I could have a little bit of a negative wave, kind of a cross of each, and then I get destructive interference. During destructive interference, the energy of the wave is converted into kinetic energy. And then as the waves keep going, though, after they interfere, they keep going as if nothing ever happened. So here's an example of constructive interference. And we're going to keep it pretty simple for this, for our unit here. But there's a lot of implications of this that we learned in different areas of physics. Here I have a triangular wave and a rectangular wave, and they're heading towards one another. Now, in the next frame right below, they're getting closer. And in the next frame, they are overlapping. And you see then the dotted lines, those are the outlines of the two waves. And we see that they're interfering, and they're constructively interfering to make the amplitude larger than either of the individual waves. And you can see there's a little triangle here, and then there's a little rectangle, and they kind of add together. And then in the next picture, now half of the triangle is past that rectangle, so it's already at the point where it keeps going as if nothing ever happened, and the other half of the triangle is still constructively interfering. And then finally, the waves keep going as if nothing ever happened. Destructive interference is pretty much the opposite. Here I have two waves. One has a positive amplitude, one has a negative amplitude. And as they go to each other and interfere, they take away. Here we see it's taking away from the overall amplitude. And in this next picture, they perfectly cancel each other out. So that is destructive interference. And then, of course, they keep going and keep going as if nothing ever happened. So that's destructive interference. So I got a quick check here. These two waves are going to approach each other. What are they going to look like? Well, I got a rectangle and a triangle, and if they're interfering constructively, it's going to be both. And then we'll see both of those amplitudes adding together. And here's a quick check with destructive interference. So I have this wave moving to the left and this wave moving to the right, and that's going to take away from it. So this becomes like lost, and that's identical to this shape right here. So we get a area of destructive interference. So one of the applications that we would get into a lot more, but it's really hard to do virtually, is this concept of standing waves. Waves that are trapped. So here I have a oscillator, and this guy's just going up and down, and this is tied off right here. And that these waves can get trapped, and the energy just bounces back and forth. And we can create these things called standing waves. Now, individual points on the string, you can see in this picture right here, they're moving up and down, right? So it's not like it's not moving, but it's moving so fast that we see it as this standing wave. And there's this nice little pattern here that tends to give us this shape. And it's called a standing wave because the crests, which are at the top, and the troughs, which are at the bottom, appear to stand in place as it oscillates back and forth or up and down. Now, when we have two waves of equal wavelength and amplitude, and they're traveling towards each other, that's going to cause some superposition, and that's where we get these standing waves from. So as these two waves are interfering, that's where the superposition comes in, and we get the standing waves. Now, some quick little anatomy of some standing waves. In a standing wave, there are some points that never move, right? Right here, right here, right here. These are known as nodes. These points are called nodes, and they're if I look at a wave, this is one complete cycle right here. So they're every half wavelength apart. Antinodes are the pieces at the top and bottom, and those are moving a lot. They have the maximum displacement back and forth, and they have to be there's two of them in one complete wave. So when we're looking at nodes and antinodes, anytime we have a node, we have no intensity. It's essentially standing still as it oscillates, as the rest of the wave oscillates. And then the antinode has super high intensity, and it's going back and forth quite rapidly. So if we're looking back at the concept of interference, then the intensity is at a maximum when we get constructive interference, and the nodes and intensity are at a minimum when we get destructive interference. So it's never really moving because the waves are always canceling each other out. So when we're making a standing wave, they can be created by a string as long as we have two boundaries. And in the picture, there was an oscillator going up and down, sending these waves out. They bounce off the wall and they come back, and then those interfere with each other. And as they bounce, they create identical waves going backwards. So that's how we get identical waves going back and forth. Now, there's a lot of ways that we can explain or quantify standing waves, but what we tend to do is we talk about the mode number. And the mode number helps us quantify the number of possible waves and also to visualize it. So this first picture up here, this is a mode number of 1. It has one antinode. This is a mode number of 2. It has 2 antinodes. This is a mode number of 3. It has 3 antinodes. So that's how we quantify the number of bumps in a standing wave. And different modes then will have different wavelengths, because a wavelength is one complete cycle, one complete up and down. So this length right here from this wall to this wall for a mode number of 2 is the wavelength. But what about this first one right here? Well, it would have to be twice as long for us to get a complete wavelength. So this wavelength here is going to be twice the length of this string. And down here, well, the one complete wave, that's right here, this is only 2/3 the length of the string. So we have a formula for that, and that's what this guy is over here. It says the wavelength of this any particular wave is twice the length of the string divided by the mode number. And a standing wave will only exist if that string has that wavelength. And that also comes where we can find these standing waves from our fundamental equation, velocity equals frequency times wavelength. So the frequency that I have these waves going up and down will determine where my standing or how my standing waves can form. So when we're creating this standing wave, the oscillation frequency has to be formed from velocity equals frequency times wavelength, and this is 2L over M, like we saw from the previous slide, where the mode number is the number of antimodes, and that's or antinodes. That's the only way we can get a standing wave on a string. We could get a lot more in depth with this. We could ask a ton of questions on this, but we're not going to, just because it is very difficult to get in this virtual setting. So here, some pictures, right? We got a mode number of 1, mode number of 2, we get 2 antinodes. Mode number of 3, we get 3 antinodes. Mode number of 4, we get 4 antinodes. That's just the standing wave. And these have to have, even though the ropes are identical and the situations are identical, these all have their own specific frequencies in order to get this to work. So if these frequencies aren't exactly what they are, then we will not get a standing wave. We won't get this constant constructive and destructive interference to make it a standing wave. So here's a quick check. What's the mode number? Well, if I want the mode number, I count the standing waves, the standing antinodes. 2, 3, 4, 5. It is a mode number of 5. Now, when we find that first frequency that causes a mode number of 1, this is known as the fundamental frequency. The fundamental frequency says that if I have this frequency, I will get a standing wave with 1 antinode. Now, what's really easy actually to if once we get that standing wave is that if I want a mode number of 3 and I want 3 antinodes, all I have to do is take that frequency and multiply it by 3, whatever my fundamental frequency is. It's 3 times F1, and that'll give me the frequency at that mode number. So this frequency it's known as a fundamental because all you have to do is multiply by the mode number that you want to see, and that'll get you those other standing waves. These are known as higher harmonics. This comes in a lot with music and instrumentation, and the sequence of frequencies in an instrument, if you're playing a brass instrument, right? So a brass instrument only has 3 or sometimes 4 valves. So you'd think there's only a certain amount of note combinations, but people who play like trumpet and baritone, right? They control the airspeed, and even if they have one note that they're playing, they can play multiple harmonics by controlling the velocity of the air. And that's how they can play multiple notes with the same fingering combination. When we're looking at standing sound waves, it's similar to waves on a string, except we take this area of compression. We talked about compression before and rarefaction, and we make compression a positive node, a positive antinode, and we make rarefaction a negative antinode. And with that, as sound waves move back and forth, those air molecules can oscillate, causing the same concept. So we can get standing sound waves, and in the lab, you're supposed to look at a boomwhacker ensemble, and they played a song for you. And in the boomwhackers, those are standing sound waves, and those air molecules are sloshing back and forth, and some of the air or some of the sound is escaping and some of it is sloshing back and forth. And that's how you can hear the boomwhackers as that air is sloshing back and forth. Now, sometimes if you look really closely, a lot of times the boomwhackers are just open at both ends. If it's open at both ends, we call that an open tube. And a boomwhacker is a really easy way to kind of look at this, but instrumentation actually gets a little bit more difficult. So if it's open at both ends, we can assume that at each end it is atmospheric pressure. So there's no area of high pressure or low pressure. So we assume that a column of air that's open at both ends has an open tube, and it has atmospheric pressure at each side. Now a closed If we close one end of the tube, then that's going to create a wall for those molecules to slosh off. So we assume that the closed end is an antinode. And that's just a way to visualize what's going on the inside for standing sound waves. So what happens is, and you guys are not responsible for this, if I have an open tube, I can get different standing waves based on how fast the air is moving. And maybe some of you had a toy growing up where you spun it in a circle and it made a noise, and then you spin it faster in a circle and it makes a higher frequency. That is producing greater mode numbers, and that's creating different frequencies. Now, if we have a closed tube, it just kind of shifts from what an open is, because we're assuming that anytime it's capped, there is an antinode of pressure. And I can have an open closed tube, and that would have a node at one side and an antinode at the other side. And if you watched and listened to the Boomwhacker choir, anytime they capped one end of the tube, it made the pitch super low. And look at this. I have a mode number of 1 here, and on an open tube, I had a mode number of 1. But on the mode number of 1 with the open tube, it is one complete node to antinode to node in that cycle. So we had a node, antinode, node. But a closed tube is just a node and an antinode. So really the effective wavelength of it becomes twice as long. And actually, to get one complete wave, it has to be 4 times the length of the tube. So when we have an open closed tube, it's a very, very low frequency. Now, in real life, we can compare 2 instruments, a flute and a clarinet. And a flute and a clarinet, they're not super different in length, right? A clarinet is not that much longer than a flute. I'm pretty sure the clarinet's longer, but it's not that much longer, but it sounds so much lower. And the reason that it sounds so much lower is because a clarinet acts like a open closed tube, whereas a flute acts like a open tube. So therefore, a clarinet has a much lower frequency than a flute does. So with standing sound waves, a couple more formulas here. This just sums up what I just talked about. You're not going to be responsible for these formulas, but similar to what we did for the waves on a string, if I have an open or a closed tube, I have a set of formulas to get the wavelengths. If I have a open closed tube, I have a different set of formulas to get where the standing waves are. And again, you're not going to be held responsible for this, but it is stuff we can quantify, and that helps us better understand musical instruments quite a bit. This just kind of summarizes everything. It's a nice, quick little cheat sheet for you for practice problems. But again, on the test, we're not going to be asking very specific questions on this at all. Now, we can also have waves interfering, and when we're looking at sound waves, when they interfere constructively or destructively depends on how far apart those waves are. So if I have, for example, if I have a speaker 1 and speaker 2 and they're in line with each other, if these waves match up with each other, like you see this orange and purple or magenta waves, we'll get superposition and we will get constructive interference. So I can have 2 speakers that make a very, very loud sound, and that would be constructive interference. I can also have waves that are out of phase with each other. And if, in this case, I have speaker 1 and speaker 2, and they're putting out opposite waves from each other. And in this case, I would get real life destructive interference, and the superposition is 0. There's no net pressure. So what do you hear? You don't hear anything. These waves are out of phase and they can cancel each other out. A great example of this is actually the concept of noise canceling or noise reduction headphones. They act as 2 speakers. We got speaker 1 and speaker 2. What's speaker 1? Speaker 1 is just the outside world, all right? So it's not an actual speaker, but speaker 1 is the noise coming from outside. Speaker 2 are your actual headphones. Now, when those are side by side, the outside world and your headphones, they see what speaker one is doing and they create an opposite wave or an anti-wave. Now, when those two waves interfere with each other, they cancel each other out. And that's why it's called noise canceling headphones, because it will reduce the amount of noise coming from the outside by producing an anti-wave to lower the overall intensity. Now, one last concept that we're not going to get very deep into is the concept of beats. And anybody who's ever been in a musical ensemble knows what beats are. Maybe you didn't hear them as well when you were in sixth grade, but when we have two frequencies that are slightly different, they have areas of constructive and destructive interference. So here's an example. Let's say that this orange wave is 440 hertz. Well, the magenta wave is moving slightly faster, right? Which means there's going to be less cycles per second. So maybe this is 439 hertz, right? So if they're slightly out of tune with each other, and this happens all the time in instrumentation, we get areas right at the start, right? Perfectly constructive, right at the end, perfectly constructive. So we get a high intensity. But as we phase away from that, in the middle, we have some areas of perfectly destructive interference, and that'll cause a very low intensity. So when I have two instruments playing almost the same pitch at the same time, we hear only one thing. We only hear one note, but it has successive loud, soft, loud moments. So it's like a wah, 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 wah. So if you ever hear that, that's two people playing slightly out of tune. These distinctive sound pattern of high or loud, soft, loud are beats. So beats, there's more stuff we can quantify with that. And again, this is just kind of an overview crash course in some of this, but the air is oscillating against your eardrum, not at either one of the true pitches. So before we had 440 hertz and 439 hertz. That's not right. 439 hertz. Well, what your ear hears then is an average of the two. So it'd be 439.5 hertz, right? So it's hearing a different frequency, but it's hearing successive loud, soft, loud moments that are based on the difference in the frequency. So this is 440, 439. We have a beat frequency, how often the beats are occurring at 1 hertz. So every second it'll be loud, soft, loud. So it'll be wow, 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 right? So that was bad, sorry. But that is if you're slightly out of tune with each other. Now, when you're in tune with each other, this formula still works, right? The beat frequency would just be 0. If we were both playing 440 and 439 hertz, our beat frequency would be 0. Now, if you're playing drastically out of tune with each other, the worse out of tune you are, the faster that beat frequency, the worse, the more loud, soft, louds you're going to hear every single second. So that's why intonation is so important. The loud, soft, louds are very displeasing to the ear. So you got some homework to complete. Homework week 4, complete this activity and submit it on Google Classroom. So you should have done lab 4 already. This lecture you just watched, and then there's just a little bit of practice. And this is the end. And this is all we're going to try to do with standing waves. There's a lot more that we could be doing. And I hope you at least learned a little bit from this flipped video series. But it is really hard to do some of this virtually when there's so many good demos and stuff that I like to show you in class. So hopefully you picked up at least a little bit. Get week 4. Let us know if you have any questions, and we will have a test next week. Don't worry, it's open note.